Okay, I'll get started with today's class. Hope you can hear me okay. Last class, we were talking about solids, some properties of solids, in particular elasticity. And in talking about elasticity of solids, we applied Newton's laws, we applied conservation laws, and we got a glimpse at the sort of atomic molecular building blocks of matter and the interactions between those atomic and molecular building blocks of matter. Going to do a similar thing in today's class. We're going to look at selective properties of fluids. We're going to look at pressure. And again, over this class and the next class, we're going to be applying Newton's laws, conservation laws, and in that way, we're going to get a glimpse at the atomic and molecular building blocks of matter, and again, the interactions between those atomic molecular building blocks. So that's the sort of general framework of what we were doing in the last class and what we're continuing on in this class, and what we're continuing on in this last module of the semester. So let me say a few more specifics about today's class. So fluids are important, or at least there's lots of important fluids. The most notable ones to me are air. Air is a fluid. It's a type of fluid we call a gas, but air is a fluid. It blankets the entire Earth, and we need air to survive. The second most notable fluid, right? Water is a fluid. It's a type of fluid called a liquid. It covers about 2/3 of the Earth, and again, it's necessary to support our life. So if you want to think about today's class and about the next class, it's really going to be about like air and water and important properties of air and water. We're going to talk about hydrostatics, which is fluids at rest. And we're going to talk about hydrodynamics, which is fluids in motion. So those are the two big categories, hydrostatics, hydrodynamics. When we talk about hydrostatics, we're going to be mainly applying the Newton's laws, and we're going to consider forces, and we're going to meet a principle called Archimedes' principle. And then when we look at hydrodynamics, we're going to maybe mainly applying energy conservation laws and looking at the energy stored in fluids. And we're going to meet a principle called Bernoulli's principle. Now, some of this stuff we're going to do today, and some of this stuff we're going to do in next class. So this is the subject of this entire week's material. Okay, so first I got to start with a few definitions, or a couple of definitions. And the two definitions are definitions of density and the definitions of pressure, because we're going to be working with density and we're going to be working with pressure. So we better define them. Now, look, I know probably in other classes, probably in like kindergarten, elementary school, you met density and you met pressure, and you already know what pressure and density are. But I just want to define them in our physics language, and then we're going to really move on after these next couple of slides to applying them and using them. Okay, so density. So when we talk about density, when I think about density, I think about some object that has some amount of matter, has some mass, and occupies some region of space, has some volume. So I'm thinking about the mass of the object, and I'm thinking about the volume of the object. And then the density of the object is simply the mass of the object divided by the volume of the object. So that's this little definition in words here over on the left. in physics, we'll normally write it as an equation, and these are the normal symbols we use. So mass is m, of course, volume is v, of course, and density, we normally give the symbol rho. And then you can see the units of density because you knew the units, the basic units of mass and volume out of which density is made. So the density, the units of density are kilograms per meter cubed because it's mass over volume. I'll just remark on a few important densities here. These are densities that we'll meet in today's class and we'll meet in the next class. Density of air. You know, when I was growing up, when I was at kindergarten in elementary school, I thought air must have no density at all, no mass at all, but that's not true. 1 cubic meter of air, which is not a huge volume of air, 1 cubic meter of air actually weighs over a kilogram, about 1.2 kilograms. So 1.2 kilograms per cubic meter is the density of air. And it's always, to me at least, it's always to me surprisingly large. Density of water, if you have a cubic meter of water, you had a tank of water for your tropical fish, right? That is 1 cubic meter. That's a heavy tank of tropical fish because that 1 cubic meter of water would weigh 1,000 kilograms. So that's the density of water. And then the most dense fluid that I know of, I think is the most dense fluid. The most dense fluid is mercury. It's that silvery liquid metal. And its density is sort of amazing. If you had 1 cubic meter of mercury, its density is 13,000, over 13,000 kilograms per cubic meter. So 1 cubic meter of mercury would weigh 13,000 kilograms, over 13,000 kilograms. Okay, so that's density. We've done that. Pressure. Let's define pressure and give a few examples of pressure, like we defined density and gave a few examples of pressure. So if you want to think about pressure, think about a surface is the way I think about pressure. I don't know if you can see me very clearly right now, but I've got a surface here. It's this sheet of polystyrene. And that sheet of polystyrene has a certain surface area. And if I exert a force over that surface area, then the force divided by the area is the pressure. And so upstairs here, that's the definition of words. Pressure is force over area. And downstairs here, that's the definition as an equation. P for pressure is force F divided by area A. Now, you can see again from the units of the quantities on the right-hand side, there's force. Well, we know the units of force by now, I hope, newtons. There's area. We know the units of area by now, I hope. It's meters squared. So the units of pressure are newtons per meter squared. Now, in memory, I guess, or in honor of somebody that we'll meet today, Pascal, we call 1 Newton per meter squared, we call that pressure 1 Pascal. So 1 Pascal is 1 Newton per meter squared. Now, let me make a remark about pressure versus force. So supposing you got a thumbtack and you press it into a cork board, right? You don't need much pressure. Sorry, let me start again. You don't need much force to push the thumbtack into the cork board. But what you do need is a lot of pressure to push the thumbtack into the cork board. And that's why there's a tiny tip, a needle tip on thumbtack. Because although you're not exerting with your thumb a big force, that force is applied over a tiny, tiny, tiny area. And so moderate force of a tiny, tiny area is a very big pressure. And so that's how you press the thumbtack into the cork board. You're using a moderate force, but an enormous pressure at the point of contact between the thumbtack and the cork board. The same is true about wearing stiletto heels, right? If you walk around with them on, I haven't done that for a while, but if I was to walk around with them on, then, well, you know, my force on the ground is the same as if I walk around with regular shoes on. It's still the force of gravity that's pulling me downwards. But with stiletto heels, you're concentrating that, you're spreading that force over a tiny area. And so it's a huge pressure. In regular shoes, you're spreading that force over a much, much greater area. So it's a much smaller pressure. And so wearing stiletto heels versus regular shoes is a large pressure, very large pressure at the heel versus a much more moderate pressure. Just a couple of numbers to give you here. The pressure of the surrounding air near the Earth's surface, near sea level, in pascals is actually 100,000 pascals. So 1 Pascal, 1 Newton per square meter is really a very small pressure. And atmospheric pressure is really enormous in pascals. It's about 100,000 pascals. It goes up and down with the weather a bit, but it's about 100,000 pascals. Supposing we take a trip to the planet Venus. That's a neighboring planet for us. Let's go to Venus. What's the atmospheric pressure on Venus? Well, the atmospheric pressure on Venus is actually enormous. It's enormous, but not as enormous as I've written here. There should be 9 times 10 to the 6 pascals. I'll correct that. So it is 90 times higher pressure, roughly, 93 times higher pressure than Earth's atmospheric pressure. If we went to Venus, right, that atmosphere would crush us. We wouldn't survive the pressure of the atmosphere. It's also extremely poisonous, so it would poison us anywhere. So I don't know whether we want to be poisoned first or pressurized first, but anyway, we wouldn't survive it. Okay. Where does the density of matter come from? And where does the pressure of fluids come from? Both the density of matter and the pressure of fluids actually come from, ultimately, the tiny microscopic atoms, molecules that the materials are made up of. I want to show you a little animation of where pressure comes from. So I'm going to change screens at this point. So here's a little animation. I find this kind of mesmerizing. I was looking at it quite a bit this morning. Imagine the black rectangle. That's a container of gas. So maybe it's some can or some box that's containing some gas. And inside the can or the box containing the gas, we're actually seeing the individual atoms and molecules. And those atoms and molecules, if we could see them, they are literally buzzing randomly to and fro and bouncing off the top, bottom, front, back, left, right walls of the box. And so that's what you're seeing here. Now, every time one of those little atoms or molecules strikes, a side of the box, a wall of the box, that's a collision. And we've talked earlier about collisions. And we know that when there's a collision between, say, a ball and a wall, and this is between an atom molecule and a wall, there's forces that are exerted. There's momentum that is transferred. And the pressure on the walls of a box container that's containing a gas or a fluid is due to these collisions between the atoms and molecules of the gas, of the fluid, and the walls of the box. So every time a little atom or molecule strikes the walls of the box, it exerts a little force and it transfers a little bit of momentum. Now, individually, those amounts of force, those transfers of momentum are too tiny to notice, but they add up, they superimpose to create the net force, the net pressure that's acting on the box. So that's the microscopic atomic molecular origins of pressure. Okay, let me go back to my lecture slides if I'm capable. Here we are. And now we've defined pressure and density, I want to talk about a very important relationship that describes the pressure and its relationship to density in a fluid. In, say, an example would be in the atmosphere. This formula would describe pressure in the atmosphere. Or say another fluid would be the ocean. In this formula would describe the pressure in the ocean. And we're actually going to kind of work out this formula for the pressure in the atmosphere, pressure in the ocean, by some little thought experiments. So I've got a couple of slides coming up now that are just little thought experiments that I didn't come up with them. Somebody else thought of them, but I'm reproducing them. And they're going to lead us to this formula that describes the pressure in a fluid, like the air, like the ocean. Okay, so let's take a look at this this slide. And the goal of this slide is to convince you, to make you a believer that the pressure at a certain depth in a fluid, at a specific depth beneath the surface of the fluid, is the same everywhere throughout the fluid at that depth. So that's a goal. And I'm going to kind of argue that with this thought experiment. So what you're seeing here in blue, let me get the pen going again. What you're seeing in blue here is, well, what could it be? It could be a glass of water. It could be a swimming pool, right? It's the water in a glass of water, or it's the water in a swimming pool, one of those two. Now, I'm looking inside that glass of water. I'm looking inside that swimming pool, and I'm thinking about a little cell of water in the swimming pool, or a little cell of water in the glass of water. It's this guy here. And in this particular thought experiment, I'm going to imagine, don't have to do exactly this, but I'm going to imagine it's a sort of this rectangular box. So now reminding me of a coffin, right? A long sort of box. And that's the cell of water. That's the volume of water I'm thinking about. And we're going to think about, the fact that that little cell of water in the swimming pool or in the glass of water it's actually at rest in there. It's at rest and staying at rest in there, which implies that if it's not accelerating up or down to left and right, or front and back, that the forces acting on that cell must be in equilibrium. And so we're thinking about that cell's at rest, staying at rest, and we've realized that means that the forces acting on that cell of water are add up to zero. Now I'm going to think about, to be specific, just the forces from the left and right that would push it left or right if they weren't in perfect balance, but they are in perfect balance. And so the cell remains at its at rest position. So this force over here on the left, I call it F1, that's acting on this surface of the cell on the left is exactly balancing this force on the right that's acting on this the surface of this cell on the right-hand side. So those two forces, I labeled them F1 and F2. Those two forces are equal in size. They're opposite in direction, equal in size, so the object remains at rest. Now, those are two forces that are acting on two surfaces, two equal size surfaces there. And so if I use the relationship for my box between force and pressure, if the forces F1 and F2 on the left and right sides are equal, then it must be that the pressures on the left-hand right side of the box are also equal to one another. And so I can conclude that P1 and P2 are equal to one another. And this sort of thought experiment, I won't go through all the details of this thought experiment, but it allows you to conclude that at a given depth in the fluid, so imagine this is at some depth, let me indicate it here, that we normally call H, which isn't a great choice because that sounds like height, but it's actually depth, D, but we call it depth H. But anyway, everywhere at that depth within the fluid, at a distance H beneath the surface of the swimming pool, or a distance H beneath the surface of the water in the glass, everywhere, absolutely everywhere has the same pressure. And so that's a key fact about pressure in fluids. So if I walk around my office right now, I'm walking around through the atmosphere. So I'm walking through that fluid we call the atmosphere. Because I'm always at the same height or depth as I walk around in the fluid, the pressure is going to be the same. So that's an important point. So let me go on to the second thought experiment. And in this thought experiment, again, I'm going to think about, say, the swimming pool of water or the glass of water, and I'm going to think about a cell of water within the glass of water or the swimming pool of water. But this time we're going to argue that if you go deeper and deeper and deeper into the fluid, then the pressure in the fluid is going to go correspondingly higher and higher and higher. So the deeper you go in a fluid, the higher the pressure grows in the fluid. The pressure in the fluid is in proportion to your depth in the fluid. So we're going to argue that. Okay, so again in blue, oops. I mean, I have to do that at least once every lecture, I guess. Okay, in blue, we got our swimming pool, or we got a glass of water. And this time, I'm going to think about this kind of cell of water inside the swimming pool of water or inside the glass of water. And it's this, now I've changed the orientation of it. Now it's like a rectangle like a coffin, but it's now standing vertically. And again, I'm going to make those arguments like that cell of water is at rest, and that cell of water is staying at rest. So if that cell of water is at rest, staying at rest, it's not accelerating. If that cell of water is not accelerating, it must mean that the forces acting on that cell are add up to zero. And so, for example, the force from the water above the cell that's pushing the cell downwards must be balanced in some way by the force from the water below the cell that's pushing the cell upwards. And so I'm going to look at the relationship between this force, F1, is the one from the water above the cell pushing down on the top surface. I'll color it in here. And then I'll look at the relationship to this force downstairs here, called it F2, is the one pushing up from the fluid below on the bottom surface. I'll color that in too. So what's the relationship between those? In the previous example, those two forces on the left and right-hand sides of the cell of water were equal and opposite. But actually in this example, those two forces on the top and bottom are not equal and opposite. And they're not equal and opposite because those are not the only forces that are acting in the vertical direction. Also acting in the vertical direction is the force of gravity on that cell of water. And the balance between the forces, the equilibrium of the forces, is that those forces on the top and the bottom, the F1 and F2, and gravity, the weight of the water, that's in equilibrium. And so that's what I'm concluding here for this vertical cell, that there's a force on the bottom that's pushing up, that's the F2. There's a force on the top that's pushing down. And the difference between the force upwards from the bottom and the force downwards from the top, that net force, which is upwards, is balancing the force of gravity, mg. And that's the equilibrium situation in this case. So again, we're applying Newton's laws. Okay, so that's an important thing. In this case, the forces on the top and the bottom of the cell of water are not equal and opposite. They're different by an amount that is governed by the weight of the cell of water. Now, in the last example, we then took that relationship between the forces and divided through by the surface areas of the left and right ends of the box to get a relationship between the pressures. And you can do the same thing. I'm not going to do it here, but you can do the same thing in this case. You can take this relationship between the forces on the top and bottom and the weight and divide through by the area and get a relationship between the pressures. Now, when you do that, you're going to use the definition of pressure and you're actually going to use the definition of density. So the two definitions we met in those first two slides of this class. But when you do that, you get this little relationship here. So instead of talking about the force difference between the top and bottom, it now talks about the pressure difference between the top and bottom. And now, instead of mg, when you divide through by area, you get this interesting quantity on the right-hand side. The rho is the density of the fluid. The g is the acceleration of gravity. And the h, in this case, is the height, the depth from the top of the cell to the bottom of the cell. So the depth of water in your cell of water. So those are those quantities. And the greater it shows you, the greater that you make h, right? The deeper you go in the fluid, then the greater the pressure difference. It also tells you, right, the greater the density of the fluid, the greater the pressure difference. And it tells you that the pressure difference is also in proportion to the acceleration of gravity. So it would be different on Earth compared to Moon, compared to Jupiter. Okay. So that relationship between pressure and depth is embodied in a principle we call, in an equation we call Pascal's equation, which also incorporates a principle that we call Pascal's principle. And that's this equation here. That's this equation here. And why do I keep doing this? There's no explanation for that. Finally, that's this equation here. So in this equation, pressure, the pressure on the right, on the left, is the pressure at some depth in the fluid. And so that's this P, pressure at some depth. And this rho GH, well, that H is the depth in the fluid. And so that piece of the equation is just what we've described, just what we figured from our thought experiments. It's pressure versus depth in a fluid. There's one extra piece that's added to this equation, and it's this P naught. If you exert an external pressure on your fluid, then that external pressure that you're exerting on the fluid, that increases the pressure throughout the fluid, everywhere throughout the fluid, by that amount. So that P naught is some external pressure that's being exerted on the fluid. So let me give you a couple of examples of that, because it sounds a little abstract, and let me make it a bit more concrete. Think about the ocean. The ocean is enclosed by, beneath it, rock and sand and whatever mud is in the ocean, and above it by the atmosphere, the Earth's atmosphere. So the ocean is really in a container where the walls of the container are the rocks and sand and mud at the bottom, and the atmosphere, the oxygen and nitrogen at the top. The pressure of the atmosphere, the Earth's atmosphere above the ocean, is P naught, and it increases the pressure inside the ocean everywhere throughout the ocean. So the atmosphere is pushing on the top of the ocean, but that pressure P naught on the top of the ocean is transmitted through Pascal's principle throughout the entire ocean to the very depths of the ocean. So that's interesting. Another example would be think about your bodies and think about the circulatory system in your bodies. So the blood is contained in the arteries and the veins. If a pressure is applied to the blood in the arteries and veins, if the heart applies a pressure, if the heart pumps, that pressure, that P naught, is transmitted throughout the body, to your legs, to your arms, to your heads. And so that's why you can measure your blood pressure by putting a cuff on your arm, or you could put a cuff on your foot, I guess. The pressure exerted by the heart is transmitted throughout the body, throughout the arteries and the veins. And then another example that we always give, a famous example we give, is that think about the brakes on your car. The way they work is there's a brake fluid, and there's a pipe containing the brake fluid between the brake pedal on your car and the brake pads on your car. And again, that brake fluid is in a kind of container. The container is made out of the cable and the pedal and the brake pad. And when you exert a force and a pressure on the brake pedal, that pressure is transmitted, that P naught is transmitted everywhere throughout the brake fluid, through the cable to the brake pad. Okay, I'm going to show you a couple of demonstrations, I think, to illustrate atmospheric pressure and the depth dependence of pressure. So I'm going to share a different screen. Okay. So in this little video, again, I'm back in chemistry physics building like old times. I'm gonna show you just how strong air pressure is, how big a force air pressure can exert. And the way I'm going to do it is basically by lifting a really rather heavy piece of wood. You can see the wooden rectangle in this video here, with a thin, very light sheet of rubber. And so we're going to see how to do this. So this is the sheet of rubber, and it's very flexible. It's just a couple of millimeters thick. And this is the piece of wood. It was pretty heavy, this piece of wood. I mean, I can lift it, but it's certainly, I couldn't lift a few of them. And now I'm going to try and lift it with this sheet of rubber. So I'm placing the rubber. I'm going to place the rubber on the wood, and we're going to see if I can lift it. I'm going to restart this. So I think that's really fantastic that with that little piece of rubber put on the top, there's no, I mean, look, there's no glue. I'm not a magician or playing tricks on you. There is no glue, there is no adhesive. I'm just placing that rubber on the very top of the sheet of wood. I'm smoothing it out a bit to get the air out, and I'm able to lift the sheet of wood. So what's going on there? So if that piece of wood was in the air, there would be air pressure on either side, the top and bottom of that sheet of wood. There would be, the air pressure on the top would be pushing it down, and the air pressure on the bottom would be pulling it up. Now, when I put the rubber sheet on top and hold the rubber sheet, the air pressure from below is pushing, literally pushing with some large force that sheet of wood up onto the rubber. And so although I'm just holding the rubber, the wood is being pushed up onto the rubber, and that's how it's being supported by air pressure. I'll show you another example. Actually, I won't show you this one. I think I'll show you this one. I'd like to say I made this video, but of course I can't say I made this video. But what you're seeing is an old railroad, old oil tanker here in the foreground. And over here in the background on the right in red, that's a giant vacuum pump. And you might be able to make it out. There's actually a vacuum cable that runs from the tanker, bottom left, to the vacuum pump over here on the top right. And they're pumping the atmosphere out of the tanker. They're removing the air from the tanker. And so normally if the tanker or a can is filled with air, right, there's atmospheric pressure on the outside of the tanker trying to push it inwards, crush it. And there's air pressure on the inside of the tanker trying to blow it up. And so normally for the tanker, there's this sort of balance between this crushing force, it's actually enormous atmospheric force from the air pressure outside, and this sort of explosive force from the air pressure inside. And they're just in this nice sort of little perfect balance. But if you take the air from the inside out, then there's just the air pressure from the outside pushing inwards. And we're going to see what happens. So here they are increasing the pressure or improving the vacuum, and then suddenly this thing collapses. Now they're doing nothing struck it or hit it or was exploded near it. They just pumped the air out from inside, and they just left behind the air outside, trying to crush it. And so it just shows you how large atmospheric pressure is, how big that 100,000 newtons per square meter is. Okay, I'm going to go back to my slides. There's a note I saw in the chat. I forgot to post this most up-to-date lecture slides. I will do that after the lecture class. Yeah, I apologize for that. Okay, I think we're done with the quiz. So the quiz asks us to compare the pressure in the fluid, the red fluid, at these three locations, A, B, and C. So this is an example of those rules about pressure in a fluid. At a given depth in a fluid, the pressure everywhere at that depth is the same. As you go deeper in a fluid, the pressure grows. As you go shallower in a fluid, the pressure shrinks. But at a given depth, the pressure is the same. And it doesn't matter. It just doesn't matter what shape the container is. So this container here, right, is this really weird shape made out of all these different combinations of funnels and U-tubes and bulbs. But each of these 3 points, A, B, and C, they're all at the same depth in the fluid. So A, B, and C are all at this depth in the fluid, i.e. they're all this same depth beneath the surface of the fluid. And so A, B, and C all have the same pressure. And that would be true if we went down here in the fluid. Each point here in the 3 tubes would have the same pressure. And that's a key feature of pressure in fluids. Okay, so now I want to just turn to, in the remaining half an hour, we'll just look through a few examples of pressure density and applications of those relationships between pressure and density, Pascal's principle that we've figured out. Okay, so I'm assuming you can, let me put the camera on just to show you this more clearly. We'll put full screen on. Okay, so as you probably know, chemistry physics is a construction site. And so what I thought I would do was steal things from the construction site. So I've stolen this sheet of polystyrene. And with this sheet of polystyrene, I'm going to return to an old question. I'm going to hold the polystyrene in my hand, and I'm going to ask this old question about what are the forces acting on this polystyrene as I hold it in my hand. Now, this is a question we asked, I think, in one of the early lectures, 4 or 5, we're talking about Newton's law. I held a object in my hand, and we asked, what are the forces acting on the object held in my hand if the object's at rest and staying at rest? And so I'm going back to that question. What are the forces on the polystyrene slab if I hold it in my hand and it's at rest, staying at rest? No expense spared on demonstrations today. So now I want to share my slides again. And here we are. So that slab of polystyrene weighs or has a mass, let me be careful, 0.87 kilograms. And I measured it, it was 1 meter by half a meter in cross section. And then it had a thickness of 5 centimeters or 0.05 meters. And I'm going to compare a number of forces that are acting on that. We're going to compare gravitational force, atmospheric force, what we call buoyant force, and the normal force that's acting on the slab of polystyrene when I held it in my hand. I should have drawn my hand in this picture, but I didn't. But we're imagining it's being held in my hand. It's staying at rest. It's at rest, staying at rest. Okay, so on this slide, I'm going to compute the gravitational force and the atmospheric forces on the top and bottom of the polystyrene sheet. I got to get the annotation going again. So we're going to calculate the weight, force of gravity. We're going to calculate here what I called Ft. It's the atmospheric force on the top of the polystyrene sheet. And then we're going to calculate what I called Fb here. It's the atmospheric force on the bottom of the sheet. And on the picture of the sheet, where I labeled the dimensions of the sheet, I've also added a picture of these forces. Now, over here on the right, that's the force of gravity, the weight. And then in red here, that's the atmospheric force on the top of the sheet. So that's trying to push the sheet downwards. That's this guy here. And then in this nice magenta here, Fb, that's the atmospheric force pushing up on the bottom of the sheet. And so we're going to calculate those three forces. There's one other number that I put on here that we need to use. Now, the point is that this sheet, like you and I right now, we're immersed in a fluid. We're immersed in the air, and that's a fluid. We're experiencing the atmospheric pressure of that fluid. Okay, so look, this is easy. The weight. The weight of the polystyrene sheet is determined by the mass of the polystyrene sheet and the acceleration of gravity. We just got to multiply those two things together. It's 8.53 newtons. The main reason I've calculated the weight here is I'm going to use that as kind of a reference point. We've got an 8.5 Newton object. How do some of these other forces, like the atmospheric force, like the buoyant force, like the normal force, how are they all going to compare to that? Okay, so now start with the atmospheric force on the top of the sheet. That's Ft. And the way I'm going to figure it is from that relationship between force and pressure. That the atmospheric force will be the atmospheric pressure on the top of the sheet multiplied by the area of the sheet. So the more pressure, the more force, the more area, the more force. Now, the pressure on the top of the sheet is atmospheric pressure. I've called it P0 here. So I just got to multiply atmospheric pressure by the area of the sheet. And we mentioned earlier on that the atmospheric pressure is 100,000 newtons per square meter. The area of the sheet is not this. This is actually a mistake. It's 0.5. That's a bad mistake because it's going to infect all the rest of the no, it's not. I'm going to get away with it. That area of the sheet is 0.5 meters squared. And so the force on the sheet is 0.5 times 10 to the 5 newtons, 50,000 newtons. That's the force on the top. Okay, so we got that, even though I made a little mistake. Atmospheric force on the bottom of the sheet. Atmospheric force on the bottom of the sheet, from the relationship between force and pressure, is the pressure at the bottom of the sheet multiplied by the area of the sheet. And so we've got to do that little calculation. And the key thing here is that the bottom of the sheet is a little deeper in the atmosphere than the top of the sheet. It's 5 centimeters, 0.05 meters deeper in the atmosphere than the top of the sheet. So because it's deeper in the atmosphere, the pressure on the bottom of the sheet is not the same as the pressure on the top of the sheet. It's slightly larger than the pressure on the top of the sheet. And it's larger by that amount rho GH that we discussed. And so the pressure on the bottom of the sheet here compared to the pressure on the top of the sheet up here, they both contain P0, atmospheric pressure, which was at the top of the sheet, but it's increased slightly at the bottom of the sheet by rho GH. And then I've just got to multiply that by the area to get the total force that's exerted on the bottom of the sheet. Okay, and that total force on the bottom of the sheet is the same as the force on the top of the sheet. That was P0A plus this little extra bit. And that's the way I'm going to write it. I'm going to write the force on the bottom as the force on the top plus a little extra piece. Here's the force on the top is 0.5 times 10 to the 5 newtons. Remember, I made that mistake. And here's the little extra piece, because we're deeper in the fluid, is the density of the fluid times the acceleration of gravity times the depth that we've gone in the fluid, which is 0.05 meters, times the area of the sheet, which is, gosh, 0.5 meters squared, not 0.5 meters. I must have been drinking red wine or something when I made this transparency, I guess. So I'll correct these two mistakes. Anyway, the final pressure on the bottom is 50,000 newtons plus this little extra amount, which is 0.32 newtons. So there's a tiny change. So stand back from this slide, and this is sort of an epiphany, I think. You know, we think about that polystyrene sheet and we think about the weight, and we say, well, look, it weighs 8.5 newtons, and that's the force that's causing all the trouble, and that's the force that I need to balance to support the polystyrene sheet. But we're ignoring forces that are on the scale of 50,000 newtons downwards and upwards on the sheet. And the only reason we got away with ignoring those enormous forces down and enormous force up due to the atmospheric pressure on the top and the bottom of the sheet is that they almost perfectly cancel one another out. So we never mentioned this. I never mentioned this. I kept this secret in, lectures 4, 5, 6, 7, when we were talking about weight and normal forces and all that fun stuff. I never mentioned that actually there's some much bigger forces around. There's enormous atmospheric forces that are acting on the objects we're considering. I never mention it because they almost perfectly cancel one another out. Okay. This slide, I want to calculate the two remaining forces. One of them we know well, it's the normal force, and the other one is new to us. It's the buoyant force. Okay, so what is the buoyant force? It's this little guy here that I put in parentheses. The buoyant force is the difference, is the name we give to the difference between the upward force of atmospheric pressure beneath the, in this case, polystyrene sheet, and the downward force of atmospheric pressure from the air above the sheet. It's the difference between the two. And it's important, the buoyant force is important because it's the bit that doesn't quite cancel out. So it's the net effect of the polystyrene sheet being immersed in the atmosphere. So if we took this, let's build a spaceship. Let's go into outer space and let's put the polystyrene sheet in outer space. There's no atmosphere above it. There's no atmosphere below it. There's no atmospheric forces acting downwards or upwards. So there's no buoyant force. In the air, on the other hand, the polystyrene sheet is immersed in the atmosphere. There's an atmospheric force downwards. There's an atmospheric force upwards. They don't perfectly cancel out. And that little remainder is the buoyant force. If we took this polystyrene sheet into the ocean, we swam down in the ocean with it, then there will be a ocean force pressure on the top of the sheet. There will be an ocean force and pressure on the bottom of the sheet. And the difference between the ocean pushing downwards, the ocean pushing upwards on the top and bottom of the sheet, that would be the buoyant force of the ocean. So buoyant force is a very important quantity when you have objects, you place objects in fluids. It's an important quantity for planes in the air. It's an important quantity for boats in the ocean. Okay, so we're going to calculate that buoyant force, and then we're going to calculate the normal force. As a reference point, again, I'm just reminding us all that this sheet has a weight of 8.53 newtons. That's the force of gravity acting on the sheet. And it's going to be useful to compare the buoyant force and the normal force with that 8.3 Newton gravitational force. So let's calculate the buoyant force. It's this difference between the slightly bigger push upwards from the atmosphere and the slightly bigger push downwards from the atmosphere. Here they are. And of course, I'm admitting I made this mistake here on these two guys. The force downwards from the top was 50,000 newtons, not 100,000 newtons. But this is why, you know, I like to get away with mistakes. And here I get away with a mistake because it cancels out on the left and right when I calculate the buoyant force. So this truly is the buoyant force. It's 0.32 newtons. So although those forces of the atmosphere from above the sheet and below the sheet were massive compared to the weight of the sheet, they were many thousand times larger than the weight of the sheet. They almost perfectly cancel each other out. And we're left with a net force due to the downward and upward forces of atmosphere that is only 0.3 newtons. That's actually quite a bit smaller. It's only a few percent. It's only a few percent of the weight of the polystyrene sheet. Finally here, I'm going to calculate the normal force. And I'm going to calculate the normal force from the fact that this polystyrene sheet, when I hold it in my hand, is at rest, staying at rest. It's in equilibrium. It's not moving and it's not going to change its motion. And so the forces that are acting on the polystyrene sheet when it's at rest, staying at rest, must balance each other out. So let's see how that works out. There's a force of gravity downwards, that's W, and downwards I'm going to call the negative direction here. There's a normal force of my hand, that's upwards, that's given the symbol N, and it's got a plus sign because it's upwards. And then there's, well, look, there's the atmospheric force up and the atmospheric force down, but they mostly cancel out and leave behind a little buoyant force. Here's the buoyant force in parentheses. So these are the three contributions, and they must add up to zero because the object's at rest and staying at rest. Now, if I take this equation and rearrange it for n, the normal force, it tells me that the normal force is the weight less the help in supporting the polystyrene sheet from the buoyant force. And so the normal force is not 8.53 newtons, the weight is 8.53 newtons less the 0.32 newtons, that's 8.21 newtons. And so that's the answer to the normal force. So, you know, for all our objects on the surface of the Earth, you know, we've been using an idea in talking about Newton's laws in the earlier lectures that the normal force often just balances the weight. In reality, the normal force is not exactly precisely equal to the weight. It is going to be slightly less than the weight because the normal force is helped in supporting the object by the buoyant force because we're living in an atmosphere. We're living in the air. Now, I picked the polystyrene sheet in this example because that's a case where there's a object that is not very dense. And because the object is not very dense, the buoyant force on the object is relatively large compared to the weight of the object. In this case, it's a few percent. If I had imagined a concrete slab or a steel slab, that buoyant force would have been essentially negligible compared to the mass of the concrete slab, the weight of the concrete slab or the weight of the steel slab. Okay, I've got a second example. I want to work through this to finish off the class. I think it's a really nice example, and it's a pretty straightforward example. As you know, we live in the atmosphere. And as I'm sure you know, the atmosphere doesn't go on forever into outer space. The atmosphere is a little blanket that surrounds the Earth's surface and keeps us nice and warm and cozy. How thick or how tall is this nice, cozy, warm atmospheric blanket? Now what we understand pressure in a fluid, and atmosphere is a fluid, we can actually estimate the thickness of the Earth's atmosphere. So this is quite an impressive thing we're doing in a way. We're not going to go up to the top of the atmosphere and find out what elevation we're at when we flew our plane up there. We're just going to sit down here at our desks and we're going to estimate the height of the atmosphere based on our physics knowledge of pressure in fluids. Okay, so what we're going to do specifically is I'm going to imagine, you know, as I say, the atmosphere is this big sort of sheet or blanket surrounding the Earth's surface. It's a big spherical shell surrounding the spherical Earth, but I'm just going to imagine a little column of it. So I'm looking out the window now towards the president's house, and I'm imagining this column of atmosphere from the ground outside is back porch up until the top of the atmosphere. I'm imagining that, and I'm going to calculate the height of that. And so in this picture here, this is, gosh. This column here, again, everything looks like a coffin today. This column is this column of atmosphere, column of air. Now, at the bottom of the column, I know the pressure is atmospheric pressure. It's 100,000 pascals or 100,000 newtons per square meter. At the top of the atmosphere, what's the pressure? Well, the moment you step outside the atmosphere into outer space surrounding the Earth and its atmosphere, that's no pressure. And so if it's no pressure outside, the moment you just get inside the atmosphere, that's essentially no pressure too. And so if you were to take a trip from the top of the atmosphere to the bottom of the atmosphere, you'd be going from top of the atmosphere where the pressure is 0 to the bottom of the atmosphere where the pressure is 100,000 newtons per square meter. And so I called here in my calculation, I'm going to call P1 the pressure at the top of the atmosphere, P2 the pressure at the bottom of the atmosphere. So P1 is the pressure at the very top of this column of fluid. P2 is the pressure at the very bottom of this column of fluid. We know the density of air, 1.3 kilograms per cubic meter. We're going to calculate the height of this column, and that will be the height of the atmosphere. That's the plan. And here's my calculation. So my calculation is based on the fact that there's a difference in pressure between the top and the bottom, because as you go from the top towards the bottom, you're going deeper and deeper in the fluid. You're going a depth h in the fluid. And that pressure difference, delta P, or P2 minus P1, the pressure at the bottom minus the pressure at the top, is determined by that equation, formula, expression that we figured out, rho GH. So if you look at that equation, well, we know the pressure at the top and bottom of the atmosphere. We know the density of the atmosphere. We know the acceleration of gravity in the neighborhood of the Earth's surface. The only thing in this equation upstairs here that we don't know is the height of the atmosphere. And so I rearranged the equation as an equation for the height of the atmosphere. The height of the atmosphere is the difference between the top and the bottom divided by rho g. If you think about it, it makes sense, right? If the pressure difference was larger, that would correspond to a higher atmosphere, a thicker atmospheric blanket. And that's because the greater pressure difference would correspond to more air above your head and greater force of atmospheric pressure on your head. Also, the height depends inversely on the density. If this was water instead of air, then a much smaller height of water would give the same pressure at the bottom of the swimming pool than compared to at the bottom of the atmosphere. Okay, anyway, all I got to do is fill in the pressure difference between the top and bottom. That's 100,000 newtons per square meter. Divide it by the density of air, 1.3 kilograms per cubic meter, and 9.8 meters per second squared acceleration of gravity. And we get this number here, that we get an estimate of the height of the atmosphere as about 8,000 meters. And we've done that without ever getting in a plane and going to the top of the atmosphere. Now, actually, that's an estimate. It's not too bad an estimate, but it's not exactly right. What is actually wrong with our calculation was that we assume that the density of the atmosphere is the same all the way from the top of the column of air to the bottom of the column of air. Whereas in reality, the density increases the deeper you are in the atmosphere. And so we didn't include that effect. So our calculation is approximately right, but it's certainly not. It's just an estimate. The actual height of the atmosphere is more like 11,000 meters. So it's higher. And it's higher because the air is going to get less dense as we go higher up. That atmospheric density, 1.3 kilograms per cubic meter, is sea level atmospheric density. And as we go up into the atmosphere, you went up in a plane or up a mountain, the atmospheric pressure gets smaller. So compare those, 11,000 meters, the true height of the atmosphere, 8,000 meters, our estimate of the height of the atmosphere, with the height of the highest mountain, Mount Everest. That's 8,800 meters. And so you can see there that Mount Everest is near to the top of the atmosphere. And that's why it's very hard to breathe if you go up to the top of Mount Everest, probably for two reasons. You're tired because you've gone up 8,800 meters, but also the air is very, very thin. You're running out of atmosphere at the top of Mount Everest. Anyway, I'm going to finish there.